Hello. So in this example, we are wanting to know when our function f of x up here is concave up or concave down. So remember, concavity is all about the second derivative. And in particular, when the second derivative is positive, it's concave up. When it's negative, it's concave down. So really, what this question is asking is to build a sign chart and record the result. So that's what we're going to do. So first step, find the second derivative. So f prime of x. Well, here we have, right, standard straight up polynomial. So we're going to do 2 times 3x to the 3 minus 1 plus 12 times 1x to the 0, which 1 minus 1. And the derivative of negative 1 is just 0. So this is then 6x squared plus 12. And that means the second derivative of x, right, bring down the 2, so I have 6 times 2x to the 2 minus 1. Derivative of 12 is 0, so this is 12x. So this is only 0 when x is 0, so my sign chart's pretty straightforward. It's just got the 1, 0 at 0, and I mean, 12x, right, it's a line with a slope of 12. So picking a negative, it's negative. Picking a positive, it's positive. So negative, positive. Well, this means that it is concave up on the interval. So concave up, right, is when it's positive. So it's on the open interval from 0 to infinity and beyond. And concave down on the interval. And here it's going to be to the left of 0, so negative infinity to 0. All right. And that's that. That's really all there is to it. So we find the second derivative, use that to find where it's positive or negative, and then record the result. That's that. Hello. So in this example, we want to know when our function f of x is concave up and concave down. So as usual, that means we want to find, right, the second derivative and see where that derivative is positive or negative. So really we want to find the second derivative and then find the sign chart for that derivative. So I'm just going to jump right in here, finding the second derivative. So f prime of x. So you can use the quotient rule, you could use the product and chain rules, whichever way works for you. So I'm going to get, let's see, x plus 1 times the derivative of the top, so that's going to be 6x minus 8 minus the top 3x squared minus 8x plus 5 times the derivative of the bottom, which is just 1, all over the bottom x plus 1 squared. Now, I could just jump right to the next derivative, but doing that means I'd have a product rule involved. So instead I'm going to expand this out and combine like terms to make the next step a little easier on myself. So here I'm going to have 6x squared minus 8x plus 6x minus 8. And then distributing the negative, so that's minus 3x squared plus 8x minus 5 all over. And then I could even expand that out, so I get x squared plus 2x plus 1. And combining like terms now, I get 6x minus 3x, that's going to be 3x squared. Negative 8 plus 6, that's negative 2, plus another 8, so that's going to be plus 6x. And then minus 8 minus 5, so that's minus 13 over x squared plus 2x plus 1. So now I can take my second derivative, And same idea, right? Quotient rule or product and chain rules. Excuse me. So bottom, so I'm going to have x squared plus 2x plus 1 times the derivative of the top, which is 6x plus 6, minus the top, 3x squared plus 6x minus 13, times the derivative of the bottom, which is just 2x plus 2, all over the bottom squared, which I'm now going to remember was x plus 1, so I'm going to have x plus 1 squared squared, which is x plus 1 to the 4th. Now I can expand all this out and, again, combine like terms. So here I'm going to have 6x cubed plus 12x squared plus 6x, so it's doing 6x against each of those, plus, and then 6 against each of these, so 6x squared plus 12x plus 6. And then here, I'm going to have minus. So I'm going to do 3x squared against both of those. So I'm going to get 6x cubed plus 6x squared. And then 6x against both of those. So that's going to be plus 12x squared plus 12x. And then minus 13 against both of those. So that's going to be minus 26x minus 26. All over the bottom squared, x plus 1 to the 4th. And finally, I can combine like terms. So really I want to distribute this negative. So I'm going to maybe write it, I'll just write one more line with the negative expanded out. So the first thing is going to be the same. So it's going to be 6x cubed plus 12. In fact, I'll combine like terms in this first part because I'm rewriting it anyway. Why not? So I have 6x cubed. For x squareds, I have 12x squared and 6x squared. So that's 18x squared. Then for x's, I have 18x. And then my only constant is plus 6. Plus. So now I'm going to distribute the negative while I combine like terms inside. So my only x cubed is this one, so I'm going to have a negative 6x cubed. My x squareds, I have 18, so then I'm going to have minus 18x squared. And then my regular x's, I have, let's see, negative 14, negative. So that's going to be positive 14x. And then my constant, the only one I have is negative 26, which is then taking a negative, so that's plus 26. All over x plus 1 to the 4th. And I can finally combine like terms. So my x cubes cancel. My x squareds cancel. That's good news. So I'm down to the other ones. So I'm going to have 18 plus 14, so that's 32x. And then plus 32 over x plus 1 to the 4th. Okay. All right. So that is then, I can actually simplify this more, and it's worth doing because I'm going to get 32 times x plus 1 over x plus 1 cubed, to the 4th. I'm jumping ahead here. To the 4th. But then I can cancel one of those, right? So this is equal to 32 over x plus 1 cubed. How is that for a nice end result? Right? It took us a while to get there, but we got there. Now what this actually tells me is there's actually a fair chance that I could have simplified this thing at the start and made my life way easier. And that would have been a nice observation to make, right? So if I had instead looked at my initial function up here, right, my, let's see, 3x squared minus 8x plus 5, right, over x plus 1. Question is, could I have simplified this? So the top I can rewrite as 3x plus 5, no, minus 5. So this is doing AC method. 3x minus 5, x minus 1 over x plus 1. And is that right? So that's going to be positive 5 minus 3 minus 5. Yep, that's correct. All right, so it didn't actually go. It was close, but not quite. So I don't feel as bad now. Of course, if I had done it like this, maybe I would have gotten some nice cancellation at the first derivative level, but I'm not going to jump into that. Regardless, I have finally gotten down to the end result, which I'm just going to sort of record since there was all this work there, which was that I got my second derivative of x, and it was surprisingly elegant, right? Surprisingly simple, x plus 1 cubed. Now remember, I want to do a sign chart, and a sign chart is where the second derivative is 0, which is nowhere, but also where it's not defined, which is -1, right? So my sign chart then is surprisingly simple. It just has -1 as the only spot I have to worry about. And again, I would take some very big negative and very big positive to test those different sides. So if I pick some giant negative here, the plus 1 won't do anything. The cube, right, if I take a negative and cube it, it's still negative. 32 isn't going to change the sign, so it stays negative. Likewise, some giant positive, adding 1 still positive, cubing still positive. 32 divided by a positive is positive, so it stays as well. And so, since this is my sign chart for f double prime, this tells me that I have concave up where it's positive, concave down where it's negative. So this thing is then concave down on -infinity to -1, and concave up on -1 to positive infinity. Okay. And it really is that straightforward. That's it. I mean, like, right, straightforward, right? This computation was a mess, but, you know, sticking with it, we got to a nice end result, which gave us a nice end result, right? Nice concavity. So that's that.